This video is on extreme values of functions, or absolute and relative maxes and mins. So here first are a bunch of definitions. First, a y value f of c is a minimum or absolute minimum on an interval I for the function f of x if f of c is less than or equal to f of x for all x in I. Similarly, f of c is a maximum or absolute maximum on an interval I for the function f of x if f of c is greater than or equal to f of x for all x in I. So those are the sometimes called absolute maxes and mins, or sometimes just called maxes and mins. So that's the largest value over the interval and the smallest value over the interval. We can also have relative or local maxes and mins. So if there is some open interval containing the point c such that f of c is the minimum value, then we say that f of c is a relative minimum or a local minimum, basically just smaller than everything near it. And similarly, if there's an open interval containing a point c such that f of c is a maximum value, then f of c is a relative or a local maximum. Again, just larger, has a larger output than everything else around it. So given all those definitions, for the graph below, what are the absolute maxima and minima? What are the relative maxima and minima? For each of these, give the points x, y for each such value. So I'd like you to think about this first, and then after you locate all of those points, what is happening in terms of the derivative at each of those points? So I'd like you to pause and think about each of those questions, and then we'll look at it together in a moment. All right, absolute maxima and minima. For that, we're looking at the largest outputs and the smallest outputs on this graph. So it looks like this is the absolute max. This is the largest output, is bigger than everything else in the graph. And it looks like this and maybe this together, maybe it's, you're just sort of looking at something not very clearly drawn, but it could be that both of those are absolute minimums if they are both at the same value. So maybe both of these are absolute mins and absolute min. And then so we've got our absolute maxes and our absolute mins. There happen to be two absolute mins, which is okay. They're both the smallest, or the most negative in this case, outputs of this function. How about the relative maxima and minima? So let's use a new color for that. So this point is larger than everything around it. Let's call that the point. It looks like that's at like negative 2.8 comma 5, and if you don't have the exact same values I have, that's fine. Again, this is just a very rough sketch. What else have we got? We've got this right here is also a relative max. So, actually, is it? No, it is not a relative max, because if we look at here, it is not larger than everything to the left of it. So there is no open interval containing that point such that it is larger than everything around it. Similarly, there is no open interval containing that point such that it is smaller than everything around it, because these are in any open interval containing it and they're smaller. These values are in any open interval containing it and they're larger. So this is not a relative max or min. So not that point. Also not this point, because that is an open circle, meaning that it's not defined at that point. So this is also not a relative max or min. And if we think about any point just below it, there is no one point there that is larger than everything around it, because we could always get just a little bit closer to f of 1 where that open circle is, and the output would be just a little bit larger. So there's no relative max or min at either of those points. But there is a relative max or min here. This is a relative min. It's not smaller than everything, but it's smaller than everything in an open interval containing it. And this is also a relative max. A relative max. It is larger than everything in an open interval containing it. So let's label all those points. Maybe this is the point 5.5, comma 1, and those two things were not relative maxes or mins, so we don't have to worry about them. But this one was, and this one was the point 4, comma negative 1 maybe. And what else? We need to also label the absolute maxes and mins. So this was at negative 7, comma 7, that absolute max, because the output is the largest of all outputs. And then we've got this absolute min. So we've got negative 5.5 maybe is the x value, comma negative 2.8 is the y value. And similarly here, we've got negative 1, comma negative 2.8. Okay, so that's quite a few points to think about, because we were also asked about what is happening at the derivative at each of these points. So let's start with all of the interior points. So, for example, negative 5.5, comma negative 2.8, and let's see, negative 1, comma negative 2.8. Those are our two absolute mins. And what is happening at that point? At that point, what is happening to the derivative? Well, the slope of that function at that moment in time, the slope is 0. And so what does that mean? That means that the derivative is 0 at that point. So f prime of negative 5.5 is going to be equal to 0, and f prime of negative 1 is going to be equal to 0 as well, because this derivative is the slope of the tangent line, and at each of those points, the derivative is 0. What else have we got? We've also got this local or relative max. So at negative 2.8, comma 5, we also have, now this is a relative max, and at that point, the derivative is also 0. The slope of the tangent line to the curve is 0. So slope 0, in other words, f prime of negative 2.8 is also 0. So what about this point, the point negative 4, comma 1, the point 4, comma negative 1. So at that point, what is happening to the derivative? There is a corner here, and there is a corner which means that the function is not differentiable. So f prime of 4 does not exist because there is a corner, and we saw before that anytime there's a corner or a cusp, the function is not differentiable at that point. The last two places where we had relative or absolute maxes and mins were here and here. So notice that this is an endpoint and this is an endpoint. And at each of those places, the function is not continuous. So for both the points 5.5, comma 1, and the points negative 7, comma 7, those were both endpoints. And it turned out not to be a relative max or a min here, but think about if this had been filled in, if 1, comma 4 were filled in, then that would be a local or relative max. And what would be happening there? So that's a place where f is discontinuous, f is not continuous, and because it's not continuous, that means f prime of 1 does not exist. Remember that if a function is not continuous, then it is not differentiable. So this could also be a place where a max or min or a relative max or min occurs anytime there is some kind of discontinuity, or more generally, anytime that the derivative does not exist. So that is a special type of point, a point where either the derivative does not exist or the derivative is equal to 0. And we call those things critical numbers or critical values. So let f of x be defined at C The value c is a critical number or a critical value of f if f prime of c equals 0 or f prime of c is undefined or the derivative does not exist. If c is a critical number for the function f, then the point c, f of c, is a critical point of f. And notice again that all the places above where we had either a absolute or relative max or min, all of those places were either critical numbers or endpoints of the function, endpoints of the interval over which the function was defined. So here is an important theorem, and we can think of our motivation for this theorem as what we just observed above. If a point c, f of c, is a relative or absolute maximum or minimum over an interval, then it must be the case that either c is a critical value, again critical value means f prime of c equals 0, or f prime of c does not exist, or c is the endpoint of an interval. So if there's an extreme value at c, then either f prime of c equals 0, or f prime of c does not exist, or c is an endpoint of the interval. Those are the three possibilities. And again, that is an important idea for us, that if there is some kind of extreme value, absolute or relative, then the derivative at that point is 0, or the derivative at that point does not exist, or c, the input, is the endpoint of the interval. However, if c, f of c is a critical point, this does not necessarily imply that c, f of c is a relative or extreme value. To think about an example of that, I'll actually have you think about the function f of x equals x cubed, and think about its derivative. Are there any places that are critical numbers, critical points for this function? And is there a relative or extreme value at that critical point? So just take a second and think about the derivative of f of x equals x cubed, find any critical numbers, and then think about whether or not there are relative or extreme values at that point. Okay, so when we take the derivative f prime of x, that's just 3x squared, cool. And so are there any places where this does not exist? No, like this is just a polynomial. F prime of x equals 3x squared exists for any input value that you could plug in. What about places where the derivative equals 0? So we could set f prime of x equals 0 and solve for x. That means 3x squared equals 0. That means x squared equals 0 over 3, 0. And so x can only be 0. So this is the only critical point. This is our only critical number. Now let's think about what happens to the graph of f of x at x equals 0. Well, is that a local max or min? No. If we look at any open interval containing it, then there are points that are higher than it, larger than it in that interval. There are points that are smaller than it in that interval. So this is not a local or absolute max or min. But this is a place where just for a moment in time, the derivative is 0, the slope is 0. So f prime of 0 equals 0, but it's not a max or min, local or relative. However, that still is a critical number. So 0, 0 is still a critical point, because the derivative is 0 in this case, or if the derivative did not exist, that would also be a critical point, regardless of whether it's actually an extreme value. So based on all of this, here is the process for finding extreme values for a function over a closed interval I. And this is only finding the absolute max and min. So this is only finding the absolute maximum and minimum over a closed interval. And in future sections, when we're looking at the first derivative and what it says about the function, we'll be able to use that to find local maxes and mins as well. So what we need to do is take the derivative of f of x and find the critical numbers that are in that interval. In other words, the points over that interval where either the derivative equals 0 or the derivative does not exist. Then we need to evaluate f at each critical number. So for each critical number, f of c equals what? And we also need to evaluate f at each of the endpoints. So f of a, if a is the endpoint of the interval I, f of a is what? F of b is what? And then after that, we just need to compare those values. So we compare those values, and the absolute maximum is the largest of these, and the absolute min is the smallest of these. So I guess really step 4 is compare. And when you compare those values, the absolute max is the largest of the outputs, and the absolute min is the smallest of these outputs. So I'd like you to use this process to try to find the absolute maximum and minimum for the function f of x equals x cubed minus 12x over the interval from -4 to 0. And this is a closed interval, so both the endpoints -4 and 0 are included. So pause and try that out. We'll talk about it together. Okay, so our first step is to take the derivative, f prime of x in this case. This is an easy one for us. 3x squared minus 12 is the derivative of that. Now we want to solve for f prime of x equals 0. So 3x squared minus 12 equals 0 means that, let's see, we could factor 3 out. 3 times x squared minus 4 equals 0. And then we could factor this piece. So we've got 3 times x minus 2 times x plus 2 equals 0. And so this is equal to 0 means that x equals positive 2 or x equals negative 2. Those are the two values that make this equation equal to 0. So these now are both critical values. Now, are there any places where f prime of x does not exist? F prime of x equals 3x squared minus 12. That's a polynomial. This exists for all x. This exists for all values of x. So there are no critical values based on the derivative not existing at a point. Okay, now we've found all the critical values. Now we need to also test these and the endpoints. So we want to evaluate f at each critical value in the interval. So don't forget that our interval was the interval from -4 to 0. So in fact, that positive 2 is a critical value, but actually it's not a critical value in the interval. So that is not a critical value that we'll be interested in. X equals -2 is the only one to look at. And so when we evaluate that, f of -2, this is in the original function, not in the derivative. F of -2 is -2 cubed minus 12 times -2, plugging it into the original function. So that is -2 cubed, that's -8, minus a negative, so plus 24, and that gives us a positive 16. So f of -2 is positive 16. Okay, now we also need to, next step, step 3, evaluate f at each endpoint. So this was our function f of x equals x cubed minus 12x over the interval from -4 to 0. So -4 and 0 are our two endpoints. F of -4, again, the original function, is -4 cubed minus 12 times -4. So that's -64 minus negative, so plus 48. and that's going to give us negative 16 as the output for f of negative 4. F of 0, that's 0 cubed minus 12 times 0, that's simply 0. And so now we have each of these values and we need to compare them. So now we're going to compare the outputs for the critical values in the interval and the endpoints. And we see that we've got f of negative 4 was negative 16, f of negative 2, that was the only critical number in the interval, was a positive 16, and f of 0, that was another endpoint, was 0. So out of all these possibilities, what we have is that negative 16, that's the smallest output, so this is our minimum. Positive 16 is our largest output, so this is our max, and therefore the point negative 4 comma negative 16 is the absolute min over the interval, and negative 2 comma 16 is the absolute max over our interval, and we are done.